Perfect. What if I talk really loud? Okay, great. So, good evening, everyone. My name is James. I'm from Grakn Labs. There's a whole team of us, quite a large proportion of the company, actually, that are here this evening. So I'll introduce you to them as we go on. So, what I'm actually going to do through the scope of this talk is I'm going to talk about Knowledge Graph Convolutional Networks. But along the way, I'm going to introduce what we actually do as a company. So what I'll try and do is disambiguate as we go which part is this work and which part is provided by the platform that our company has built. So let's go off to a start. So let's see if we can get this. Is this working? Good. Excellent. So the big question that we're trying to answer here is, how can we move intelligent systems? We try and stop short of always saying artificial intelligence, because we know that in the domain, people think that's a bit funny, right? Because everyone thinks when you say artificial intelligence, you talk about general intelligence. That's not really what we want to do here, okay? What we want to do is we want to take where our systems are at the moment, often they're machine learning systems, and we want to see how can we improve on what we can do right now. And what we tend to see is that there's a lot of focus in one area, but maybe we're missing some directions that we could focus on. So if we start, what are the problems with the way we do machine learning at the moment with our cognitive systems? And what we see is, typically speaking, we see that models that people build for machine learning have poor generalization across multiple domains. What we see is that we can't transfer one learning system from one domain to another, both in terms of the exact system, but also how the model works, the kind of system that we've designed. We design it purposefully for each domain that we work in. We also see that when we encounter a hard problem, we basically got two weapons that we can throw at that problem. We either have big data, throw more data at the problem and hope that it can learn more based on this, or we can increase the complexity of our learning model, both of which are not ideal. Now, what we see is that we can notice a couple of areas where we can be a bit suspicious of how we do things currently. And the areas of suspicion is that when we use these learning pipelines, what we typically do is we take the data that we have, which is maybe it's already in a tabular format, but the reality that it represents is normally not flat, okay? It's normally dynamic. It's normally something very interrelated. We flatten it and we produce arrays of numerical values in order to put into our neural networks or whatever it is that we may be using. And what we can suspect here is that maybe we're missing out on information. Maybe we're missing out on something else that we can benefit from, so that we don't have to use the weapons of big data or more complex networks, which is often only available to a big company like a Google or a Facebook. And so smaller companies, small to medium-sized companies, will often struggle to find the resources that they need, both in terms of data or complexity, to compete with those big companies. So what can we do to get around these problems? Well, what we propose is that we can take a step back and look at, well, why do we think that still humans are in general better than machines at these jobs? They just can't scale. We can't scale humans as well. So what is it about human abilities that machines don't have right now, that our cognitive systems don't have? So this is a really rough diagram of brain function areas. Okay, so if there's any biologists in the crowd, then don't pick me up on this one, right? I'm granting myself some artistic license here. Okay, but the general idea is that there's an awful lot of skills that we have as humans, and we have dedicated areas of our brain for each. Now, a lot of these we can probably do without, okay? We're not looking for the machine revolution. So let's move out basic emotions. We don't really need our machines to have that, okay? We can move out skilled movement, coordination, vision. Certain parts of this is typically not necessary for the kind of business technology that we may want to build. Well, normally we're talking about software, so that strips out a lot of the skills that humans need. But what's left that is relevant to the systems that we want to build, okay, the tools that we want to build, that we have as humans that they do not. And we propose that largely we're talking about these 3 points. We're talking about learning, reasoning, and long-term memory. So learning, we're already somewhat familiar with, but we'll go there first and investigate this. So what does the learning space look like right now? If we were to Google learning, machine learning, and see what we get, automated learning, well, we get an absolute raft of techniques that we can use. Oh, skip one too many. Anyway, we get an absolute raft of techniques that we can use to solve a problem using learning, okay? We've got SVMs, kernel tricks for SVMs, neural networks, k-means, k-nearest neighbors, Gaussian mixture models, linear regression, whatever it is. Like there are more than any person can keep track of methods to do machine learning right now, okay? So we know that we can create some kind of complex solution to get machines to learn. And we know that this space has borne a lot of fruit, that this has been worthwhile, that this has been economically a great investment. But, and actually we can go a step further, we can look at all of the providers that we have in this space. Okay, we can see that this space is really well catered for. Like if you want, whatever it is that you want to build, you've got a library that can help you do that, typically free and open source. So this area has really been looked at, right? We know this. That's why I'm guessing a lot of people here are even here. In fact, can I even get a show of hands at this point? How many people are involved in machine learning or data science here in the crowd? Okay, great. So I'd say that's about half of our audience, right, is already involved. So we see that there's a lot of jobs, there's a lot of fruit, there's a lot in this space. So if we go back to these 3 areas, which we've highlighted as what we think is important, we can say we've kind of done learning, okay? We've looked at this space. It's not complete by any means, but we know what we're doing in that space. What about reasoning? Now, what do I even mean by reasoning? What I mean is a logical process, okay? An automating logical process. Could we give that to our machines? Can we get them to automatically arrive at conclusions the same way as a human would, without having to have learned over some training set of data, right? So in this space, Prolog is about the only thing that anyone's heard of that does anything. And typically that was sort of a passing mention in some university courses. I've been unkind to Prolog here. It's not popular. It's not popular. Now, why is that? Is it because what it does isn't useful? Or is it because it doesn't present it in a useful way? That people don't immediately look at it and see the value of what it does. So I'm starting to drop some hints about what it is that we might do at this company along the way, right? So if I was going to give you some kind of example, what we're actually going to do in this talk is I'm going to be elaborating on one very specific data set. I'm going to just introduce it bit by bit, and then hopefully it will make a bit more sense as we bring it around to the end. But if I were going to give you like some sort of biological example, in this case, we're talking about animals, okay, an animal species. And what we do here is we introduce the taxonomic tree that sits above this species, which is a fin whale. Okay, this is a whale at the bottom of this tree. Now, you don't need to be an expert in this domain. You don't even need to be able to understand. I can't understand the words that are on this tree, okay? But anyone, I guarantee that anyone in this room, if I give you this information, and I also I put it as part of a larger tree, okay? And I ask you, what order in a taxonomic tree does this species Balaenoptera acutora strata, which order does it belong to? Whether you pronounce it right or not, you'll tell me the answer is Cetacea, okay? Now, what is it that you're actually doing to get to that conclusion? Now, the information that I've given you in this diagrammatic form is that this species, I'm not going to say it again, okay? This species belongs to this genus Balaenoptera, okay? And the genus belongs to the family Balaenopteridae. The family belongs to the order, and the order belongs to the class. But I've given you each of those pieces of information in this diagrammatic form as pairs. I've told you nothing directly about the species relationship to the order. So what is it that you've actually done mentally if you make the jump to say that this species is a member of this order? Well, what you've done, or the way we think that you can rationalize this, is to say that you've got some kind of rule that you've applied in your head. Okay, you said that when some set of things occur, which is to say that the species, we're going to call it A here, right? We call it some variable A, has some supertype B, right? Some parent taxon, and that group, that taxon, has some supertype C, which is this family. Okay, then in that case, you'll be able to tell me that A is also a part of this family. Okay, so we have when A and B and C, then A and C, right? Now, what that means is you've been able to infer this extra information, which is this connection. But you then can go a step further from that, and you can say that if that's true, then this family must also be a member of this order, and the species is a member of the family. So that means the species is a member of the order. And that's how you arrive at the conclusion. Obviously, you can just do this for as long as this chain might go on for. And what we call this is a kind of transitive logic. So what does this mean? What this can mean is that if we start with some amount of information, which is all of those pairwise connections that I gave you, that as humans, what we've been able to do is we've been able to use the process we call deduction to take those facts, apply some kind of logical rule that we have, some kind of logical knowledge that we have on top of those facts, and from them we deduce more facts with the dotted line here. And from that, we can apply more and more rules on top, okay, until we have a great deal more facts than we started with. But the idea here is that what we can do, what we'd like to do to automate this, is to say that we only want to store these facts that we had originally. We then want to infer the new facts from these without any real extra expense. We don't have to have a data set that sits this big on a hard disk. We can have a data set that sits this big on a hard disk. That's the idea. So how can we actually get machines to do that process for us, right? That's the question. If we can see that there's some benefit, this is the next question. And the answer we have is symbolic automation. Now, this isn't a new thing, okay? The idea that we take a programming language as the format for us to talk to a machine, right? But what we do here is we do something to be able to formally define the kind of logic that we've just seen. And we see that it follows the same kind of semantics that we already used. What we do is we say define, oh, this is not, okay. We say define some taxonomic ranking rule, okay, so that I can say exactly which rule I'm talking about. And basically, we're just following through. We're just saying exactly the same thing. We have some super taxon A, which is a parent of some taxon B, and we actually describe here what we call a relationship, which is the members inside this bracket are related, and they're related in the form of a taxonomic hierarchy. So that is, we're saying that A and B are in a hierarchy, B and C are in a hierarchy, and therefore A and C are also related through that hierarchy. So what we see quite clearly from this is that in order to actually implement this, that we're going to need some kind of structure to our data, right? We don't want to include as any of A, B, or C in this rule something that can't belong to a taxonomic hierarchy. We can't just take any old A, B, and C and infer these relationships. We don't want a building, right, to be part of a taxonomic relationship. It doesn't make semantic sense. It doesn't make sense. We know that the rule only applies in these certain circumstances. So that means we need to structure our data somehow. We need to be able to validate that the logical rule we have can be applied to our data. So hold on to that thought, because that's relevant to what I want to talk about next. So we've covered reasoning and how we might try and approach that, given that there's not much work already done in that space. What about long-term memory? So if we talk about human long-term memory, it sounds like something along the lines of what we have as a database right now. Okay, if we were going to imagine a part of our computational system that says long-term memory, that sounds like the database. But we know that, at least for most of us, what we have stored in the back of our head doesn't look quite like that, right? We know that we store the mechanics of our memories is neurons in the brain, and that it's extraordinarily complex in the way that it's connected. We end up imagining this is more like what the inner working of our brain looks like, right? That we have some nodes more important than others, okay, some less important, and that the connections are not a complete web. Not everything is connected to everything. Now, this is hard to search if you don't have some structure to that data. And I think in some places in the humans, we imagine that we have structure. We have, oh, I remember this particular thing in this category, right? We can remember it this way. But we also have the fact that sometimes you walk into a room and you totally forget why you were there. So if we can avoid that kind of instance for our machine if we know exactly what we're looking for. So what we aim to do here is, again, I'm kind of dropping hints as we go, but we can try and define some kind of structure for the data that we might input into such a memory. And so here we've got, I know it's not short, but this is quite simplistic in all of the concepts that it gets across. We see here that this defines the example that I already showed you. But I showed you that we have some taxonomic group that's called a taxon, that has a name, that this taxon also plays a taxonomic group. We'll come back to that in a second. What we also see is all of the types of taxonomic group that we saw just now. We saw that we have species, genus, family, order, class. We also see that each of these can be related through this hierarchy. We see that because hierarchy relates a supertaxon and a subtaxon. Now, this is some kind of connection between these groups. And semantically, we can say that very easily, and we can say, well, okay, it relates some supertaxon and subtaxon, so now we have a direction to that connection. Then we can say, well, okay, so what happens if we have a species? There shouldn't be a subtaxon to a species. Species is the lowest that we go in the tree, and in this data set, order was the highest that we went. Sorry, class is the highest that we went. So then we can see that class only plays supertaxon, and that species only plays subtaxon. All of those in the middle can play both, because they can have something both beneath them and above them. So then we know that we have logical integrity when we add this. We can't possibly add a genus as a subtype, beneath a species in this tree. What we can also do is we define something here which pertains to the example that I want to show you as we go on, which is to say that we have some item of animal produce that's been traded. So that's what we represent here with this entity. We say traded item sub-entity, and we say that plays this role member item. So now we have another relationship. So we can actually link some object that we've encountered in the real world and point at the taxon that belongs to, which doesn't have to be species. In this data set, it happens that it almost always is. But it could just be linked to the genus or the order if we don't know exactly what species that item belongs to. But we can see here that we can structure the data heavily so that we should be able to apply those logical rules on top of that in an automated fashion. That's the key point here, right? So what we've also introduced you to here is the entity relationship attribute model that we follow as a company here. We call it Grakl, which is Grakn's query language. Okay, and so what we've already been introduced to is all three of those types. So we have relationships, typically events or actions. There's something which brings together some collection of actors, some collection of parties that are connected in some way. We have entities, okay, that can sit self-contained and their existence is not dependent on anything else. And we also have just a very simple example there, which is name as an attribute, which is the actual values that we want to attach to things that we encounter. So that's trying to give you a little bit of a backdrop to say, well, this is how we could build long-term memory in a context that allows us to apply logical reasoning over that automatically. So the idea here is we're going to switch over to a demo, and I'm going to show you briefly what this kind of thing looks like if we actually try to interrogate a system like this. Thank you. We're going to try and keep the demos to a minimum because of the setup that we have here. It's a little bit tricky for us to Okay, great. So it's important that I introduce quickly what it is that you're even looking at here. What you're looking at is a desktop application called Workspace that's been released by Grakn. And what this allows you to do is to directly interrogate our backend database. So what you're doing is you're directly talking to a database through this interface. There's no other programming going on, right? So what you're going to see I'm actually going to pull up some queries from up here that I've saved earlier. We're going to run them, and what we're doing there is we've issued this command, this query to our database, and then we see what it is that we get back. Okay. So, that's what I'll show you. So, what we have here is an entity, which you saw just now, which is the traded item. Okay. And what we can interrogate across the traded item all of the different attributes that item owns. So in this case, we have some categorical values. We have the fact that this type of item that was traded is slightly macabre, but it's skin pieces. And okay, let me make sure I get the zoom right. There we go. It's much more gentle now. Can everyone see at the back? Yeah, great. So this is just to give you a quick visualization of how we can interrogate the back end of the database. What I'm also going to do is I'm going to expand here. Now I've double-clicked on this entity, and what our visualizer does is that allows you to interrogate all of the connections that entity has. What other things is it connected to in the database? Now this is actually built as an exploratory tool that lets you look into your database. You don't intend to use this at massive scale, but it allows you to investigate individual instances that occur in your data to actually inspect that and see what can be going on. And what we can see here is that this item that we have in this data set has quite a lot of connections. Okay. And what we can see is that this item has some relationship to a species. And that species, we already encountered, sorry, this connection, this relationship, right, which is of type taxon membership. So that's the thing, this is the relationship that links any particular item with which is the species that it belongs to, which is that it's originated from, right? Now, how do we know that that is the species that it's originated from? How do we know that? Well, in fact, what we have there is we have a hard fact. We know that this is a relationship. Now, spot the difference if I show you, for instance, the question we asked earlier, what order does that belong to? Now, we found the order which has the name as we expect, Cetacea. You can ask that to appear on the graph here. but we find that the connection between the item that we've asked for and the taxonomic order is actually an inferred relationship. Now, what does that mean? What we're trying to indicate here is that that logical reasoning that I showed you earlier has been performed here, that we didn't actually insert this fact that links this item to this order. This is not present in the database. So how do we know that it's there? Well, what we can do, we have a nice little tool here that's going to be able to tell us why this is here. So we can ask it to explain itself. We can get it to interrogate itself. Okay? And what we see here is that there's some connection between the order and the species. And that's why the order has been associated with the traded item, because this species is a part of this order. But is a species directly part of this order? Is this fact also in the database? If we look, no, it isn't. Okay, so we can explain this as well. And we find that the genus is part of the order, and the species is part of the genus. And that's how we make that connection. Well, the genus isn't directly part of the order either. So we can ask for an explanation of that. We find the family. So we can see the web of connections that's actually going on under the hood, that's taken those pairwise facts that I gave you and then inferred this summary. If they've been able to infer, to ask the question that we asked is, what is everything that the item is connected to? And the answer is a summary of all of the facts that you put as input, and with the logical reasoning applied over the top, the facts that we could derive on top. Okay, so I think what we'll do is we'll revert back to the presentation now. It takes us a moment to switch. What I'm going to do is I'm going to try and get you guys to take a little snapshot of this in your head so that maybe we can not come back to this later. It's because this is data that we exploit with the machine learning that we're going to do. Okay, so maybe we'll be able to skip out coming back to the demo a bit later on. I can't. Perfect. Do we have to skip through from the beginning?
Okay.
Not a problem. Okay, let's go. Oh, he's doing it. I'll race you. Okay, great. I'll go from there, that's fine. So we got through long-term memory, okay, and we decided that it might be a good idea, and that it might be a good idea to build that in this structured way so that we can automate machine reasoning on top of that. So, and I've talked you through this example, great. So now we've covered all three of these parts. Now, if we think these are really going to be useful, what we need to do is we need to escape what we've currently been doing as an industry, which is to just focus on one of these skills at a time. Because we know that when we're doing that, we're missing out the others. So we also don't want to focus only on reasoning or only on long-term memory, because this only gets us so far. So really what we're looking for here is some kind of way to be able to combine these three. So what do we see fitting into the slots of these three that we can find as machine components that we can put in their place? So for learning, we have a learner, okay, which could be any number of different types. We have, for a reasoning, we have some kind of reasoner, okay, some sort of automated reasoner. For long-term memory, what we choose is a knowledge graph. Now, obviously we're biased, but we think that this is the best way to be able to represent all of the kind of complexities of knowledge and really directly map a domain into some kind of data source. So what we want to do is we want to get all of these three things talking to one another. And there's a bit of a challenge. But what we also have is, I mean, we're gonna ask the learner to actually talk to the reasoner, and the reasoner just sits in front of the knowledge graph, right? So where we could directly ask questions of the knowledge graph, we want to put the reasoner in the way, so that then on the way back, the reasoner will infer anything that should exist, that we know can exist, based on the facts that are persisted in the knowledge graph. This is the idea. So what we do is we have an implementation there that sits in the middle, right? And that is the language that I've already started to show you. We call that Grakn. I've already mentioned this. So this is Grakn's query language. Now Grakn, the company here that I'm here representing, right? What Grakn provides for you is both the knowledge graph and the reasoner. You don't need to do anything to get the two talking to one another. They're fully integrated. Right? This is why I said I'm biased. Right? So the idea here is that if this is all packaged up for us, okay, because these two symbiotically do well to sit together as components of a backend, then what we have is Grakn as an interface to be able to query both the knowledge graph and the reasoner. So now what we need to do is we need to develop something, okay, that can do the learning on top of this, that can do the learning over something that is graph shaped, and not just graph shaped, but knowledge graph shaped. You can probably see where I'm going with this. So what we have is knowledge graph convolutional networks, right, which we've implemented in TensorFlow. Now, I'm going to start by caveating this. This is not a silver bullet. This is not an absolutely one-size-fits-all project that's going to solve all of your problems, right? That's not what it is. But it's our first step. It's our first attempt at trying to make something that integrates all three of these things, okay, in some sort of relatively seamless way, and in a way that what I'm about to present to you in terms of the KGCNs is a generic approach, where what you should only have to do is to change some parameters and to be able to walk around the knowledge graph of your own domain and perform the kind of learning that I'm going to show you. So what's the general idea? The general gist here is that we need to build some kind of bridge to machine learning. Now, people don't just want to do the machine learning I'm going to describe over the knowledge graph. They may have their own pipeline, okay? They may have their own interests. So what they want to do, in this case, in our example case, we have these animal items that we're interested in at the moment, and the species that they're in, where they were traded between, this kind of thing. So what we can do is we can issue something like this kind of query, where we say, get me some of these animal items. I want to interrogate what they look like. And we can feed these into Grakn, feed this query into Grakn. And what we get out is some set of results. Now we can change this query. This query can look however we want, okay? It's as if we're just querying the knowledge graph directly. That's all we're doing. We just say, give me the things that I'm interested in and describe them in a query. Once we get them back, we pass them automatically into the knowledge graph convolutional network. And what that's going to do is it's going to talk back to the knowledge graph, which also includes the reasoning engine, and it's going to interrogate the area around these concepts. It's going to say, what does this concept, what do these results look like? And what do their neighbors look like? What do their connections look like? Because just they themselves is not enough information. We also need to get information about where they sit in the graph, both on this small scale and on a big scale. What kind of role do they play in the whole of our domain? So that means that they go back to that, knowledge graph, ask these questions, and then try to learn some output matrix, where each row of that matrix is what we would call an embedding for each of the concepts that we saw here. So what this lets us do is it lets us find a way to transition from a knowledge graph, something which doesn't have a very defined shape, okay? We have structure, but we don't necessarily know the shape of our data. And we don't know any other way to build up some kind of representation that's numerical, that's vectorized, of each item that sits in the knowledge graph. That's a hard thing to do. That's not trivial. How do you greenfield go about doing that? Instead, we try to provide something. We try to say, this is one possible way to summarize everything that a concept means in the knowledge graph in a single vector. And this is then a very familiar format for anyone in data science and machine learning, because they can feed this into whatever pipeline they want to do with it, right? They now have some summary vector that they can use whatever machine learning tools they want to on in order to infer whatever it is they want to. So this is the general idea. What we're trying to build here is demonstrate how you can build a bridge from knowledge graphs to machine learning. So I'm going to delve into the actual approach. It's going to get kind of technical, but we'll try and whip through it at reasonable speed. I know that some of you will be super interested. Some of you may not. We'll see. We'll see what happens. But what we're doing here is we're adapting work that went on and was published last year at Stanford. This has been the basis. This has been the core basis that was proved to work over a generic graph, not a knowledge graph. So what we've done is taken that, furthered it, and adapted it over to knowledge graphs. So let's say that we start with some node in our graph. Okay, it could be some relationship, some attribute, some entity, something that's sitting in our graph. In general, we call them a concept. So we start from one concept, and we want to create this representation, this vector representation of that one concept. So how do we do that? Well, the obvious thing to do, as we talked about, is to look at its neighbors. So I labeled 1 for its one-hop neighbors. What we also get when we do that is we may get some connection to much further away in the graph, but that our automated reasoner can join the dots, okay, and say that this is connected to this concept. Even though the raw fact wasn't there, we can infer that fact from all of the other paths that we can see through the knowledge graph. Okay, and you get that immediately, as I showed you already through Workbase, that when we ask for the immediate connections of some concept, what we get back is also inferred connections. So we've got that for free. So once we've found these neighbors, what we really want to do is we want to say that as an animal item, what species, order, etc. that it's part of plays a large role in defining what that concept should look like. If we want a vector representation of this item, we want to have implicitly in that vector, somewhere stored in that vector, what species and order it's from. So that means we have information at these neighbors. What we want to do is we want to aggregate that into the center. So the method that we're going to use to do that, I'm actually going to describe in the next slide. I'm going to finish describing this whole approach. So the idea is we've got some aggregation process there that gets you down from the neighbor information down to one vector to represent all of those neighbors. But what about the information that we had at that central node? Okay, we also have some vector of information there. So we're going to also perform some sort of combination step that's going to combine those two vectors, okay, which may be, I'm using obviously something very small for this example, these may be very large. We need to lower the dimensionality there. So we have some combination step that we do there as well. We have these two steps, and what's going on in these steps is the information that we have available is quite rich, because even for this one of these points to exist, when we're in the scope of a knowledge graph, we already have what type of node this is, what type of entity or relationship, whether this is a taxon, whether this is a species, an order, a family, whatever it might be. It might be a name, it might be an age, it might be any of these kind of values. If it's an attribute, as we call them in Grakn, then it also has a value. Okay, age has 52, name has John, right? Whatever. All of this information plus the characteristic that is this connection, the type of connection that it has. All of these things are stored in a knowledge graph. So we have all of that information. So it's very rich. So even from just the shape of this graph, without any actual raw data, if you like, if you're talking about values attached, we can already learn quite a lot about what this central concept looks like. So having done that, the thing is, we may only get so much information from examining the neighbors just one step away. We may be missing important information that's further away. But this approach can basically be performed recursively. We can actually not do what I just explained. We can start instead at the two-hop neighbors 2 steps away. They have a representation. We can aggregate their representations, okay? We can combine them at the one hop neighbors, and then we start where I explained to you just now. Or we can go from 3 hops away, and as we hop in, each time we perform the same process, aggregating information and making a vector at each neighbor as we move further in, okay? And eventually we end up with this single representation at the center that encompasses all of the information that we saw from however many steps we're willing to take. So this is the general framework that we have here, is the combination and aggregation of information. So what we're going to do is we're going to look at exactly how that aggregation step works, just in brief. But what we're doing is, to keep it roughly consistent with the last diagram, we've got, say, 4 neighbors. Each of them has some information that we encode into a vector. And in turn, one by one, we pass them through some one-layer neural net, okay? Nothing really deep here. It's literally a single layer, okay? And these are the corresponding outputs to each of those neighbors. Now, if we want to combine these, this lets us do learning across those and decide which the important parts of them are. But if we want to combine them, then we need some operation that doesn't care which order they're in. Because in a graph, we don't care which order our neighbors are in, because we haven't stored that in any specific way. So we need to just take them out in whichever order, in some order agnostic way, some way that doesn't care. And one of the operations that we see that's really good for that is max pool. That will condense you from 4 vectors down into 1 vector, no problem. And in general, keeps a good amount of information, takes away the important points. So that gets us from our neighbors each having information as a vector to 1 vector at the point of interest that summarizes all of those neighbors. So once we've done that, now we've got this last step, which is to take the information about our neighbors and combine it with the information we have about ourselves. So that's actually quite a simple operation. We just concatenate the 2 together, and then we basically do some kind of dimensionality reduction on that, where we multiply it with some weights matrix. We may or may not use some activation energy as an output also, and that lets us define how big we want the combined output to be. So this gets us to a point where we can now use the aggregation step to combine the information of our neighbors. On top of that, stack it with the information about ourselves and apply a transformation to that. And now we have a way of creating that representation. And now we can recurse that process for as many hops as we want to. So what I've tried to do here is to summarize what the whole approach is of how our software is working. And then we can go back to the Tensorflow model, and I can show you a little bit more about how that works when we zoom out a little bit. So overall, what we see here is, in the pink box on the outside, is what your application might look like. So in general, what you're going to do is you're going to start with some sort of data import. You're going to have some data source that's going to feed in, okay, and you can manage that through there's multiple clients that we can use in Grakn, Java, Node.js, Python are the major 3. In this case, obviously we're doing machine learning, so obviously we're working in Python. Then we can pull in the data through some script, use the Python client to feed that to Grakn to populate our knowledge graph. So that's going to be the starting point. And that's where we start here with my animal example, is we have all of this data already ingested into the knowledge graph. So following that, what do? Well, we provide the query, the kind of query that I showed you just now. So we ask for some animal items, some of the stored items in the knowledge graph. We get back the concepts. We feed them into the interface for the network. And the interface is then essentially going to interrogate that knowledge graph via its own Python client. Okay, so it's, again, there's this clear divide here between where the machine learning is taking place in KGCNs and reasoning and knowledge graph storing is taking place in Grakn. And what it's going to do is it's going to interrogate what are your neighbors, what are your neighbors' neighbors, what are your neighbors' neighbors' neighbors, however far it is we want to go. And it's going to take all of that information, lift that. It's going to convert this into arrays. Okay, there'll be multi-dimensional arrays at this point that we then need to feed into our TensorFlow model, because TensorFlow, most of our machine learning frameworks, as we already talked about, only accept arrays. So we need to work with that format. So we get into that format, and then we process the model. Okay, and from the model, what we get back is either performance results if we're training or evaluating, or a set of predictions if we're predicting. So this is the scope of how this thing works. And I think that the main takeaway point here is that there's a very clear divide between what it is that the actual database offers, what the knowledge graph offers, which is the reasoner and the storage, and what it is that KGCNs is doing, which is a library that you can download from GitHub, right, that you can integrate into your application in order to use it. So what I've now done is introduced how we actually get the data into TensorFlow, just in brief, which is to basically flatten the output that we get from interrogating the knowledge graph. And we have some set of arrays that represents all of the different hops that we've taken from the furthest out all the way into where we started. And essentially, all we're doing here is we're doing these two steps that I talked about, which is the aggregate and combine. Okay, so we take the two hop neighbors that are out here, we hop into the one hop neighbors, we combine those. Then we hop in again, we combine those. Okay, and once we've done this, we combine back with the actual targets. Okay, the target here is of all of the concepts that we were initially interested in. And once we do that, what we've got out is the embeddings that we wanted. So now we've got, at that point, a representation in vector format for each of the concepts that we asked about. So this is really the key point. This is the dividing line where we see that that would be the consistent part of KGCN that you would want to use in all applications. But what we do specifically here is we need some way to actually formulate a loss function. We need something to optimize in order to make this learn. So what we do is we feed this into a dense layer. Now, in this case, I'll elaborate in a minute, but we're going to predict one of three classes. And that dense layer, which is just, again, it's very thin, right, is going to do that prediction based on the embeddings. Following that, what we're going to do is we're going to use softmax cross entropy to calculate a loss. That's the difference between the outputs of this dense layer and the labels that we provide along with our concepts. Okay, so that's how the actual learning is used. Now, what we see is that this section can be swapped in and out. It's really minute. It can be swapped in and out for whatever purpose-built task you may want to accomplish. Or perhaps one of the circumstances that you want is you actually want to do this whole process unsupervised. You want to create generic embeddings so that you can generically transform your knowledge graph into embeddings and then use them in your machine learning pipeline. So that's on the cards. That's something that we will work on in the future to get to that. Because in this way, you don't have to optimize to one specific goal. So finally, I'm coming around to the actual example that we've worked on. I've shown you a lot of hints of what it is, but the reality is what we're looking at is data from the Convention on International Trade in Endangered Species. So this organization is set up to protect endangered species worldwide, and so they record imports and exports, what we call in general exchanges, of animal-based produce. Now, it's actually not specific to animals, but for this example, I'm going to say that it is, right? And so what we find is this is quite a sparse graph but heavily interconnected data. Okay, because one species will be the basis for many of the animal items that are traded. So the general sort of plot line that I want us to follow is to say that we're some sort of enforcement agent that's looking for suspicious activity that's occurred in the trading of endangered species. So the first task that we have, if we're in this role, okay, is actually to decide which are the endangered species. So that's the task we've actually set up this demo to do, is to use knowledge graph convolutional networks over this data set, over this rich interconnected data set, to try to estimate, to predict which species are the most endangered. Now, the endangerment level for each item is a category, which is a number between 1 and 3, where 1 is the most endangered, of which there are about 900 species worldwide, and 3 is sort of your average house cat, something like that, right? I think it's probably not quite that extreme, but we'll go with it. So I think at this point, what I might do is I might try to show you, now we've got a flavor, I think I do want to do the demo again, briefly, just to show you, in fact, just to bring up exactly the same screen that we saw before, which I know sounds like a bit of a waste of time, but I think it's worth the point, make the point. Now that I've explained the workings of the KGCN project, that we just examined what it is that we were already looking at previously up on this screen, okay? So we have some traded item, okay, which is the item of interest, and we want to categorize that item according to the endangerment level of the species that it came from. And what we can see is that the direct connections, countries, and those countries here, we can interrogate what these are, and we see we have, for instance, in this case, Iceland trading with Spain. Okay, so the idea here is just to point out to you that this is the kind of data that this network can traverse. It can start at the animal item and traverse outwards to get to those first connections. From each of those first connections, it can go further and further as far as we think we need to go to capture all of the information we need. Okay, so what I'll do now, I'm just thinking where I sit in the slides, switching this back and forth. Oh, we have to skip ahead now, eh? We have to skip through. Okay, never mind. Let's see how fast Laurent is on the mouse. That's pretty speedy. Perfect. No, you did it for me. That's great. Yeah. Okay. So, what I want to present is the results that we managed to get from this. Now, we can see the raw results, and I put it in the console because I thought maybe you'd believe me. But we obviously haven't come up with something that's too ludicrous here. We've got 71% accuracy. It's worth pointing out at this point, this project is in its infancy. This has been going on for about 3 months or so. This is really early days. This is our first prototype. This is the second presentation we've given on this work. We intend to release it on GitHub either by the end of this year or early next year for people to play with. Okay, it'll be open source. And so this is not heavily tuned. This is not heavily tuned to this particular data set, which is, I think, quite a good thing, right? Because the idea is we hope that people will take this to their own domains and use it across their own domains. I don't know how many people here are familiar with the confusion matrix, which is a really great way to see how well it actually did in a very raw sense. And what we can see is that if the actual class was 1, in this case, that means the endangerment level was 1. So this is the most endangered species, 900 species worldwide. If the actual class was 1, then the predicted class was 1 20 out of 30 times. If it was 2 predicted, okay, that only happened 9 times out of 30. And if it was 1, if it was predicted as 3, where the actual class was 1, then it only happened 1 time. Okay, so this makes another point, okay, which is that in this case, we only asked the database for 30 items of each class. Now, in almost any field of machine learning, that is an exceptionally small training data size. But what we've been able to do is benefit from the fact that each of those is heavily interconnected to much more data than it just has about itself. Okay, so that means that we can infer this. Okay, we can understand more about what's actually going on. We actually have understanding when we start to learn over reasoned knowledge. So what we go back to, I'm sorry, Lauren, because there's another demo coming. What we go back to is the overall architecture. And we say, well, okay, so great, we've got these predictions of what the endangerment level is. So if I'm the enforcement officer, right, we're taking the enforcement officer role, what do we want to do next? Well, once we've figured out what's in danger, we better figure out who's threatening to make those species extinct. Okay, there must be someone out there who has this job, right? Someone has to do this. So how can we do that? And how can we do that in an automated fashion? So the idea is if we have these predictions that have come out where we've predicted a label, then what we want to do is we want to use those predictions. We want to make them work for us. But what's the best way to do that? Well, actually, the best way to do that is to actually feed it straight back into your knowledge graph again and use the predictions you've made to augment the knowledge that you already had. So what we do here is we start to find a way to write more schema, which we can actually do on the fly with Grakn. We can actually write this schema with our existing data already present. We can add more types that we want to add to the schema. So we add some other types. So I'm not going to skip through all of those in great detail because I'm going to show them to you visually in a couple of slides. Okay, and then what we can do in these steps here, what I do is ingest back into the database the predictions that we had, and also critically what we put back in is the scores that are associated with those predictions. Okay, so I've predicted that something's endangerment level 1, but how certain am I that that's really the case? If I want to put that back into my knowledge store, then I'd better also include how certain I am about my conclusions. Otherwise, I start to put in things that are seen as fact, which may be fiction. So I think what I'm going to do, is I'm going to just do one demo to summarize these two slides. So hold on to that. That's going to be demo number 1. Okay, it's going to be how do we take the labels that we already have, that we predicted, and put them back into the knowledge graph. The second demo that I'm going to give you is when we actually put on our investigative hat and we say, where's the suspicious activity in this knowledge graph? And what we can see here is that we can actually again introduce new elements to the schema. And what we're going to call it, we've got some kind of relationship, right? So that's some kind of event or action. And what the action that we want is some detection of suspicious activity. So what are the two things that play some part in one of these detections? Well, we have some cause for us to be suspicious, or some set of causes for us to be suspicious, and we have the actual activity that we're suspicious of. That's what we're saying in this statement. And we say that we're going to be suspicious of an exchange. We could have a cause of suspicion, which is the type of item that was exchanged, and the other cause of suspicion could be the endangerment level. That doesn't make sense yet until we start to write the rule, because what we want to do is we want to find endangered meat. Because what we shouldn't see, if we just describe it in the sentence first, what we shouldn't see in our data is endangerment 1 level animals, the most endangered species on Earth right now, being traded for the purpose of meat, right? So we can be pretty suspicious if we start to find any of that in our database. So what we want to do is we want to automatically infer that we are suspicious based on those facts occurring at the same time. So what we say is if we have some item which is endangered to the level 1, and that type of that item is meat, and we also pin down the exchange in which that item was exchanged, that could be an import or an export between countries, then create a detection, because in this case we found something that's endangerment level 1 and has been traded for meat. So in this case, set the cause of the suspicion to the endangerment, the other cause of the suspicion to the fact that it's meat, and the thing that's suspicious is the exchange. So we create this new relationship, this new link between all of these 3 things. And we can do that automatically across the whole of the database, and then start to look through those results. Obviously, we can make more rules like this. Okay, it doesn't just have to be for meat. Okay, this could be for any commercial purpose. right? We can also chain that on top of one another and say that something's even more suspicious if some other conditions apply. And that lets us ask in one question of our knowledge graph all of the instances where this applies. So what I'm going to do is I'm going to be the bane of Laurent's life and ask him for the cable again so that we can do it. Thank you. Okay, let's put in. So what are we going to do first? What did I say we were going to do first? I said we were going to look at, okay, first, we're going to jump back to the slide before the last one. I know you want to see what the suspicious activity was, but we've got to go back and do this bit again. So what we're going to do is we're going to look at the results from KGCN that have been ingested by our application back into the knowledge graph. And what I've done is I've just ingested 2 results back, just to keep it super simple. So we've got 2 results that have been found. For these 2 traded items, both of them have been found to be endangerment level 1. That's how they've been classified by KGCN. Can we see it out of the back? Okay. So what I also promised is that we can put that information back in a way where we can also retrieve how certain we are about that information. So I'm going to go back to another of my pre-prepared queries. Again, obviously you can write these dynamically for yourself on the fly, but we have to do this in presentation. So endangerment level with source, I call it. We run this query, talking again directly to the database with none of the machine learning involved. And what we can see is that we've stored in the database a KGCN model. We actually represent the work that we did, not just the domain, but the work that we did, which was to build this model. We ingest that into the database so we can also track what code it was that we used to actually develop these predictions. And now we can see that the ownership, this is a has connection because this traded item has this endangerment level, right? But we can also see that that has connection is actually defined here as, and we can see more richly then the information that concerns it. We can see that it's involved in a relationship. It's involved in what is called a value prediction. So we can say that we have this full record of how this connection was formed, and that it was formed with a prediction score of 0.71. We can also see exactly what the version was of the model that we used. And this is totally flexible, so this is totally dependent on your pipeline, but we know that we have all of the information stored that we have about this conclusion. So it means that when we write the rule that I've showed you about a suspicious activity, we can also factor into that rule that we only want it to flag up over a certain certainty. When the prediction score is only over some certain value, that only then show me the results. We're not going to do that right now, but what we're going to do is we're going to jump to the second demo, which I showed you, which is looking for suspicious activity. Oh, there it is. And you can see, I think it's a really good example here, that all I'm looking for here is 3 things. I ask, find me some exchange. Exchange is an action, so that's a relationship. Find me an exchange which relates some item. So that's why we see the item here defined inside the relationship. Find me an exchange that's linked to some item, and find me the exchanges, right, that are involved in some sort of suspicious activity detection. Okay, so find me all of those things. We just press go, and what we get very quickly is the results back. So we see endangerment level 1, type meet. So these are the things we asked for in our rule. So we expect that this is a suspicious activity detection. Make sure that's bigger. Right, so that's some detection that we've inferred. We know that this is inferred. Okay. So we know that this is some, well, it's in this case an import, which is a type of exchange. We see that it's between these two countries. We see that this traded item is the one that's involved. So if we start to interrogate this, we see that indeed it is this item that has both this meat, this type meat, and this endangerment level 1 that led us to be suspicious of this exchange. I don't know if that makes sense, but the idea here is that this point has only been inferred based on the fact that it encountered these criteria all occurring at the same time. So this item starts to look really suspicious, right? And this exchange starts to look really suspicious. We found that automatically straight away from the database. So we can start to dig deeper now. We can use this inspection tool to actually start looking at, well, why did this happen? Why was an endangered species traded for meat? Now, the providing country, we have a quick look and interrogate what information, what attributes we have about that, is Sweden. Now we know it participates in this treaty. Now what's the item type as well? We can ask that. Well, we find that the item type, if we actually look, where's this originated from? What kind of animal are we talking about? We can ask about this species, Balaenoptera. Oh, do you see the linking? It's really nice. Right? I still can't pronounce it, but this is the fin whale that we started off with, right? So that fin whale has been traded for meat. It's moved from Sweden. I should almost get you to place bets as to where in the world you think this went. The answer is the United States of America. So someone packaged up some fin whale meat, which is an endangered species, and sent it to America for meat. So how did we end up with this information? What's really happened here? And actually, when we interrogate this data a little bit further, there's a couple of things that we've hidden that we haven't actually put into the knowledge graph in full, so that we get a bit more of a surprise here, right? We have an item purpose P and an item source I that are both attached to this traded item. Now, what I can actually do is I can refer to the documentation that comes from sites, from the treaty, that tells us what it is that those codes mean. Now, of course, we can ingest those into the knowledge graph, but it just seems like it's less fun. And what we see here is that the use for this was personal, right? So this was just someone who wanted to put some endangered whale meat on their table in the US somewhere. But we also see, which is perhaps the more heartwarming part, that this was confiscated, that this item was confiscated, and presumably this is how that's been logged by sites. This is how this information has come to our attention and how it's ended up in our knowledge graph. But it gives us a basis as that inspector to start to look into why was that traded, where did it come from, where are the major routes where this trade is taking place. Okay, so that concludes that demo. I think I need to buy you a beer in a bit. So hopefully that gives you some sort of a flavor for how you can take what might be quite an unwieldy data set where you can't see the wood for the trees to start with. There's so much information, but you can use this reasoning to filter down very quickly to find the information that you're interested in. Oh, straight there. Fantastic. Right. Aha. So, to start to summarize what we've done, we've looked at how we can combine these kind of 3 human skills and see if we can use those 3 in combination to actually try and simplify how we currently do data science and machine learning, but to also at the same time do something where we can trust a bit more in what's happening, where we can actually inspect what we've done and see whether it starts to make sense in the real context. So to finalize there, what I want to do is just to run through the things that Grakn does to start with, which is that it provides the schema, this structure, so the knowledge that we've imported. It provides the automated reasoning over the top of that knowledge. And also, we actually have a whole section which I haven't touched on at all in this talk, which is our distributed analytics. So I suggest, as I'll tell you in a minute, you can query our team about that after the talk if you want to hear more. And what you've also seen, you've seen several examples of this, or multiple across the talk, which is the high-level language, which is Grakn. What we hope you see from this is that it allows you to make really complicated questions distill down into code, but code that's quite easy to read. So what does KGCN do? Because this is a very separate project, right? This is a library, this is a Python library that you can use in your project that queries Grakn, that does some things for you. So what is it? Well, we hope that it will be data agnostic, time will tell. But we hope that certainly for multiple projects, we'll see that you can just apply this pretty much out of the box and start to see some results. This is an inductive approach. So as you've seen, we've only asked questions ever about the concepts that we're interested in. We don't have to build something that spans the entire graph to do our learning, which is how a lot of graph learning approaches go. So that's a huge benefit in terms of being able to use this approach on what might be a vast graph, but just pull out the elements of interest to us. We want to build this as a bridge. We want you to be able to do your own downstream learning off the back of the KGCN. So we built that in, okay, so that we should have a swappable components on that to swap out the classification or whatever you may need to do in order to fit your use case. And finally, that this is a piece in the puzzle that combined with Grakn starts to make things look a little bit more human in terms of the abilities that we can give to our system. So, I'm rounding up now. I think you've heard enough from me. If you want to follow more about what we're doing, then do get on our Twitter. You can go to our website, grakn.ai, and go to our community page. You can see our Slack, our discussion forum. There's a blog post on this, which is high-level stuff. You've heard more detail than that right now. But the blog will be updating with all the technical details. We'll be pushing out notifications when we're releasing the software. And there is one more item on the agenda. There is a selfie. So this is something that we do. I know, hopefully you won't all cringe, right? But we really like to show that people actually come along when we have an audience, that we actually talk about something real, that there's free pizza at our meetups, that's all there. Yes, ladies at the back, you in? You in? Yeah, we're in, okay. Okay, good. Okay, let's make it happen. All right. Okay, hey, Laurent, you're not in. You're not in. How many can I get in? Okay, I can get the whole room in. It's going to be good. It's going to be good. Okay, can I get thumbs up for Grakn? Can I get thumbs up for Grakn? Let's see, does it work? I'm not in it. No, we're doing one more. Yeah, I know. But it's 2018, you're allowed to take a